Okay, it is about 6:01, so are y'all ready to get started? I see one person who said no, so once again, still appreciating your honesty. How about other people? Other people ready to get started? Okay, yep, there we go. We have people saying yes in chat. I saw a thumbs up, so let's go ahead and get started. This is the fourth class of MBA 501, Analysis Using Information Systems. So what are we doing today? My plan today is to cover chapter 6. So we started probability with discrete variables on Monday. So today we're going to continue with covering probability with continuous variables. As mentioned on Monday, this is putting together some of the building blocks, I guess gathering some of the building blocks for inferential statistics. So a lot of what we're doing right now is just learning the conceptual, the theoretical basis. So then once we move into once we move into inferential statistics, these things will make sense, that I won't be springing these concepts on you at that point. Then also I'd like to cover sampling today. So I'd like to cover chapter 7 today. So we will see if that happens. If we should at least start it. We'll see if we cover the whole thing. But first, I would like to note that don't forget that homework 1 is due on Sunday. So that is due Sunday at 11:55 p.m. Also, 2 notes about that, because I've had students ask about this. First off, you only get to submit your assignment once. So once you hit that submit button, it will be automatically graded. You cannot redo your homework assignments. I do not do that in this course. So you get one chance to do it. And I will open the homework for review after the deadline. I don't want people submitting it, seeing what the right answers are, and then sharing it with their classmates before the deadline. So I will open it for review after the deadline. Those are my only notes before starting class. Do you have any questions or comments about anything? And also I do have the chat window open. So if you have any questions, type them in chat. I will be able to see it. So going once, going twice. Okay, and before I forget, I did contact IT about our audio issues. Our IT person said that no one else has had those issues, so hopefully it was just a Monday Zoom thing since Zoom was messing up for everyone. I guess complaining did result in me getting a microphone, so I will have a microphone. So if that was an issue with the camera, then hopefully the microphone will fix that. So knock on wood, hopefully that won't happen again. So someone said, on the homework, does it matter if we use decimals or percentages? So that's a very good question. I prefer decimals. I think it's by default in decimals. However, if you enter your answers as percentages, it will mark it wrong, but I will go back and correct that. So if you do your homework and you answer it in percentages and you get a bad grade, don't worry too much about it. Shoot me an email if you're really worried. But I will go back after the due date and fix all the ones that entered percentages and mark that correct if it should be correct. The reason being on Canvas, I can only mark one answer as automatically correct. So I have to put either percentages or decimals as the auto grade. So if you put one of them and it seems like it marked it wrong when it should have been correct, let me know. I'll go back and fix it. And I'm going to do that anyway after the deadline. The other question was, can we have a redo the first go around on the homework? Because I did not know that for the first assignment. That's a tough question. I don't think I ever gave y'all the impression that I would let y'all redo the homework. That's not really a graduate student thing. So my first instinct is no, because I never said that. But I will think about that further. I will give that more thought. But first impression is no. I looked at the grades. I think the worst grade so far has been like a 90. So that's not going to impact your final grade that much. But if you're really worried about it, shoot me an email. We can talk about it. Worst case scenario, if grades are low at the end of the semester, I'll give extra credit. But if you're worried, shoot me an email and I'm happy to talk about it. All right, any other questions or comments? Awesome. So let's go ahead and start. We're talking about chapter 6. Hopefully this will go better today. Hopefully my audio will not drop. Okay, yeah, just send me an email if you're really worried about it. I'll double check the grades. And like I said, the lowest grade so far is like a 90, so it should be fine. But okay, so let's start with chapter 6. Like I said, on Monday, I felt like I was a little distracted because the audio kept dropping. Hopefully today is going to be smoother. Hopefully today will be clearer. I think I should be able to express things better this time. So today we're going to talk about probability again and probability distributions again. So if you liked Monday's class, then you're in luck. We're going to cover that type of stuff more. To start, So we covered this on day 1 or 2, discrete random variables versus continuous random variables. So can anyone just give me a reminder of what is a discrete random variable? What is a discrete random variable?
Doesn't it have a countable number?
Yes, I think I heard that correctly. Yeah, it can assume a countable number of distinct values. So a discrete random variable can assume a countable number of distinct values. And I see someone got it there in the chat, so good job. So then what is a continuous random variable? What is a continuous random variable?
It has an infinite number of possibilities.
There you go, exactly. Has an infinite number of possibilities, an uncountable number of values. Good job, those 2 people in the chat. So it can assume an uncountable number of distinct values within a range. So that's not always the case. Sometimes it could be infinite, but it could be within a range. So therefore, if we're talking about discrete probability distributions, we're talking about probability distributions where we know what the possible probability or what the possible values are. So things like rolling a dice, if we're talking about a discrete probability distribution. So rolling a dice, we could get a 1, 2, 3, 4, 5, 6. Things like flipping a coin, things like taking a card from a deck of cards. But today we're going to talk about continuous probability distributions. We're going to talk about continuous probability distributions. And that's when you have certain associated probabilities, but there's an infinite number of outcomes it could be. And that might sound counterintuitive, that might be confusing, but it'll make sense by the end of the day. Hopefully it'll make sense within 30 minutes. But that's going to be our focus, is continuous probability distributions, which can have an uncountable number of possible outcomes, but they can have associated probabilities. Once again, sounds counterintuitive, it will make sense. All right, another thing we covered on Monday was when each outcome for a discrete variable has an equal chance of occurring, this is called a discrete uniform distribution. So when each outcome for a discrete variable has an equal chance of occurring, this is called a discrete uniform distribution. And this is the figure we looked at before. I guess it's a little bit different, but in this example, we have 10 possible outcomes. Each of them have an equal chance of occurring. They each have a 10% chance of occurring. So this is a uniform discrete distribution. So once again, this is a discrete uniform distribution. Sorry about that. This is a discrete uniform distribution. We have 10 outcomes, we can count them, and they each have an equal chance of occurring. This, however, is what a continuous probability distribution would look like. This is what a continuous probability distribution looks like. As you can see, it has, there we go. As you can see, sorry, I'm getting the draw tool. There we go. It has a smooth line that describes the function. So we're not looking at bars anymore. We're looking at a smooth line that describes the probability function. And as you'll also see in this example, we have this shaded area. We have this shaded area. And we'll talk about that in a little bit. But the idea behind this is this overall probability distribution function. So this continuous distribution has an associated probability. But we can also figure out the probabilities within certain ranges. We can also determine the probabilities associated with certain ranges. So we could identify, well, between point A and point B, what's the probability of landing somewhere in this gray area? What's the probability of landing somewhere within this gray area? And we can figure that out with continuous probability distributions. That's how they work. So although we can't just pick a single point and say, what's the probability of that exact point or this exact point? Instead, what we do is we identify the probability associated with an entire range, So not looking at points, not looking at exact outcomes, but now we're looking at ranges. Okay, clearing all that. So some things to know about continuous probability distributions is the probability density function is notated by f of x. So that's just basic lingo you should know, is the probability distribution function. So something like the gray area is notated by f of x. And the probability density function is the probability that a value will fall within a certain range. So the probability density function is the probability that a value would fall within a certain range. So if I asked, what's the probability density function associated with between 1 and 4 on this continuous variable, then the answer, that associated probability, would be the probability density function. So once again, talking about ranges, so such as what's the probability of falling between a 2 and a 4 on this continuous variable, that would be the probability density function. So once again, not saying 2 or 4, but saying between 2 and 4. Okay. Other important things to know is the entire area and the entire possible probability density function will equal 1. So the entire area and that entire possible probability density function will equal 1. So therefore, in this figure right here, I'm talking about everything underneath the entire slope. So everything underneath this entire slope right here is going to equal 1. So not just the gray area, but every possible value you could get is going to equal 1. So clear that. Let's go back. Okay. Another thing you should know is the lower and upper bounds of this function are usually notated by A and B. Then when you're talking about probability density functions, and I'm asking you what's the probability associated with this density function, the lower part of that function is typically notated by A, and the higher part of that function is typically notated by B. So if I'm asking you what is the A of the probability density function, that's the lower bound. And if I'm asking you what the B, that's the upper bound. Or if I give you a question that says, determine the probability associated with this density function, A equals 2 and B equals 4, you should be able to know that, oh, he's talking about the lower boundary being 2 and the upper boundary being 4. So once again, the lower bound typically notated by A, the upper bound typically notated by B. And I just realized I've been drawing all over this thing and y'all cannot see that at all, can y'all? Can y'all see that? You can? Okay, good, good, okay. Good, okay, y'all can see that. So thank you for letting me know. Okay, all right, so upper and lower bounds notated by A and B. So once again, looking at this, so that's what this would be talking about. So this would be the lower bound of the probability density function I'm interested in, and this would be the upper bound. So I could ask you a question, if there was associated probabilities with this, what's the probability of landing between A, and you would automatically know that's the lower bound, and B, and you would automatically know that's the upper bound. Of course, I would have to give you a lot more information for you to figure that out, but that could be a question. What's the probability of falling between A and B? Okay. Any questions about that so far? Okay, good. Let's continue. Okay, so the simplest continuous distribution is the continuous uniform distribution. So the simplest one is the continuous uniform distribution. And if you understood the discrete uniform distribution, then you're going to understand the continuous uniform distribution. So if you understood it for discrete, you'll understand it for continuous. So the continuous uniform distribution assumes that all values within a range have an equal probability of occurring. So it says that all values within a range have an equal probability of occurring. An example of this might be if I call a repairman and they said they might come between any time between 2 and 3, then we would assume that there's an equal chance of any of those times occurring. So therefore, the distribution, and you'll see it on the next slide, I believe, but I'll draw it right here, would look something like that. That this would be 2, and this would be 3, and the repairman could come at any time between that point, but we wouldn't have any reason to believe that any time between 2 and 3 would be more likely than another time. We have no reason to believe any time between 2 and 3 is more likely than another time. So the probability of any time between 2 and 3 is equal, so therefore it's a continuous uniform distribution. And once again, this is just visualized by a complete flat line. And in this case, we have a beginning to it and an end to it. So when you're thinking about continuous uniform distributions, you're thinking about completely flat lines on a chart. Okay. One thing you should certainly know about it is symmetrical around the mean. So that just means if we were to draw a line at where the mean is, continuous uniform distribution is going to be symmetrical around that. That everything on the left side is going to be a reflection of everything on the right side and vice versa. So it's symmetrical around the mean. Everything on the left side is a copy of everything on the right side and vice versa. Another way to think about that when I'm saying the word symmetrical around the mean, or the phrase symmetrical around the mean, is if you were to print this on a piece of paper and then fold it at the mean, everything would fold on top of itself. It would like fold perfectly. That everything on the left side would fold on top of the right side and they would correspond to each other. Okay. These are things you don't have to know, but they're just there for your reference. You could calculate the mean of that function, a plus b divided by 2. So if you have a continuous uniform distribution and you need to find the mean, the formula would be a plus b divided by 2. I'm not going to require you to know that, but it's there for your reference. And you can calculate the standard deviation through this formula right here. Once again, I'm not expecting you to know that, but if you ever need that for a reference, if you're ever on Jeopardy, there you go. So, okay, so you can continue. Once again, this is what a continuous probability distribution looks like. As you can see, this is almost identical to what I drew. We have a flat line, and we are saying that at the lower boundary is A, the upper boundary is B, and any point between A and B has an equally likely chance of occurring, has an equal likelihood of occurring. And also, this is once again for your reference. I'm not expecting you to know this for a test, but we could calculate the height of that function by calculating 1 divided by b minus a. So we could calculate it pretty much 1 divided by the range. So if you wanted to get the height of that line, you could calculate it by 1 divided by the range. But I'm not requiring you to know that. Okay. Next thing we should know about continuous probability distributions is the most important thing you should know about them. As we already learned about the most popular one. Can anyone guess what the most popular continuous probability distribution is? What?
Normal
I think someone's trying
distribution.
to answer, but it's on mute.
Normal distribution.
I couldn't hear that. Can someone say it louder?
Normal distribution.
Yeah, normal distribution. Normal distribution. Yep. So the most popular continuous probability distribution is the normal distribution. So whenever you're thinking of the normal distribution, you should automatically click and think, oh, that's a continuous probability distribution. And once again, this is the distribution that underlies most of our statistics, really. Anything that we're going to calculate later in the semester is going to assume that your data follows a normal distribution. So it's going to be extremely important that we know what that means. What is the normal distribution? Because our analyses are going to assume that our data follows a normal distribution. And once again, this is what it looks like. It has a mean. If we're looking at the standard normal distribution, which this is what this is, even if it's not standard, it does have associated standard deviations, and it has associated percentages that fall within these standard deviations. So as we see here, and this is the more complex version I showed you all very briefly yesterday, this version shows that between the mean, so the mean being right here, and 1/2 of a standard deviation below the mean, we're going to have about 19% of our data fall there. Once again, between the mean and 1/2 a standard deviation above the mean, we're going to have about 19% of our data fall there. Then if we go from the mean to 1 standard deviation below the mean, we have to have 19 plus 15, which is about 34. Same over here, 19 plus 15 is about 34. So therefore, if we wanted to calculate how much falls within 1 standard deviation, plus or minus, it's 34 plus 34, which equals roughly 68%. And we could do that for any combination of standard deviations, and we'll talk about that later today. That if we wanted to, we could ask ourselves, well, how many people fall within -2 standard deviations and -3.5 standard deviations? We could ask ourselves, how many people fall within 1 standard deviation and 2.5 standard deviations? We could ask all of these combinations. And that's one convenient thing about the normal distribution, is it lets us estimate those probabilities very easily. It lets us estimate those probabilities really easily. And that's going to carry with us all throughout the semester. All right. But but simple facts you should know about the normal distribution is, first off, the normal distribution is bell-shaped and symmetric. You should certainly know that. The normal distribution is bell-shaped and symmetric. If sometimes you hear people refer to the normal distribution as the bell curve, this is what they're talking about. It's bell-shaped and it's symmetric. So once again, if we were to draw a line down the middle, everything on the left side reflects everything on the right side and vice versa. And if we were to fold it down the middle, everything would overlap with itself once it's folded. So once again, bell-shaped, it looks like a bell, and it's symmetric. Everything on the left is a reflection of everything on the right, and vice versa. Next thing you should know about it is it is completely described by two parameters. It is completely described by two parameters, and that is the mean and standard deviation. So the shape of the normal distribution is always going to be the same. The shape is always going to be the same. So therefore, if you're assuming a normal distribution and you know the mean and standard deviation, you can model the shape of your data. You can assume a shape of your data just based on the mean and standard deviation. Or I guess you could also model the distribution of your data would be another way to put it. So if you're assuming a normal distribution and you know the mean and standard deviation of your data, you can model your data, you can estimate those percentages because the normal distribution is completely described by those two parameters, mean and standard deviation. And the last thing I want you to know about it is asymptotic. The normal distribution is asymptotic. Just now I realized that maybe my volume's quiet and that's why I can't hear y'all talk sometimes. Let me turn that up. Okay, so question for the class. What does it mean when something is asymptotic? What does that word mean? Any guesses?
Never fully reaches zero.
There you go. Yep, it never fully reaches zero. Perfect answer. That if we're looking at the normal distribution, this is zero right here. So let's draw the X and Y axis. And the bell curve looks something like this, where it's going to be a bell, if I could draw better. And on these tails, they're going to keep going out to infinity, but they never actually reach zero. They never actually reach zero. And that's what asymptotic means. It never reaches zero. It's never, ever, ever going to reach zero. One implication of that is if we're talking about a normal distribution, if we're assuming a normal distribution, theoretically, someone could have values that go out to almost infinity. Someone could have values that go out to, theoretically, it could be infinity, because they never reach zero. There's never a probability of zero associated with anything on the bell curve. So even if something went out to something like 1,000,000 standard deviations above the mean, theoretically that could happen if you're assuming a normal distribution. The probability of that would be, lower than the number of atoms in the universe or something like that, but theoretically it could happen, theoretically. So that's one thing you should know is the normal distribution is asymptotic. It never touches zero. So that means if we're assuming a normal distribution, nothing has a probability of zero. If we're assuming a normal distribution, nothing has a probability of zero because these tails go out for infinity. All right. Any questions about those 3 points, those 3 things you should know?
I have a question.
Yes. Mm-hmm.
So say we're looking at a range, like say the values are from 0 to 100.
Okay.
Is it possible for that to be a normal distribution, even though there are actual endpoints?
Yeah, that's a good question. So in those cases, we would assume a normal distribution. Theoretically, like it couldn't perfectly fit a normal distribution, theoretically. There might be times where it would look something like this, where you might in your data have a normal distribution and all of these values might fall between 20 and 80. And you have nothing that's over here and nothing that's over here. But even in that case, theoretically, if we're assuming a normal distribution and that there's a firm cutoff of 0 and 100, theoretically that doesn't fit the normal distribution, even if you don't observe any values that approach those cutoffs. So that's more of like a theoretical question, I guess, or a theoretical answer. But the answer would be that no, it would not be a perfect normal distribution. But often you can still assume a normal distribution. Often our statistics could still model that if there are cutoffs. It's just not going to 100% follow the normal distribution, or theoretically adhere to it is probably the better phrasing. Did that answer your question?
Yeah, I have a follow-up. So is it possible, say you have a mean of 90, but a standard deviation of 7? Well, then wouldn't, say, 2 standard deviations away take it above that, like, say, 100 range?
That is completely correct. Yep,
Okay.
100% correct.
So even though you can't have a value above 100, you would still theoretically get a value above 100.
Yes, and that's because in a data set like that, what you're probably referencing looks something like, let's say the max is 100. The data might look something like this, where it kind of approaches a normal distribution, but then is a little bit off. And if we were to model a normal distribution over top of that, it would perhaps supposed to look more like this. where it would actually go above that point. So that means that your data is going to be a little bit skewed. That means the data is a little bit skewed. That assuming a normal distribution in this case doesn't work out 100% correctly because your data is a little bit skewed and it doesn't fit that normal distribution. Sometimes that can still work out, sometimes it doesn't. It depends on the context. But for the purposes of this class, if you had something like a homework assignment and you noticed that was indeed the case, if you were to point that out, then I would be very happy about that. I would be very pleased with that.
Okay, thank you.
Yep, thank you for your question. And one thing that does touch upon something we briefly talked about last class, so this would be a good point to bring it up. If you ever have an instance where you're assuming a normal distribution and you know the cutoff is something like 100, and if you're assuming a normal distribution, 2 standard deviations is something like 80 to 105, then yeah, that can certainly happen. That means that your data is slightly skewed. That means that if you're to assume a normal distribution, it might not perfectly fit, but you might have done your analyses correctly. If you have something though where you know the range is something like 0 to 100, and you assume a normal distribution and it falls within something like -300 to 400, then that means you probably messed up your analyses. Your data would have to be so unbelievably skewed in that case. If you know the actual range is 0 to 100, and assuming the normal distribution, it says 2 standard deviations below and above is -300 to 400, that's so drastically different that just skewed data probably wouldn't make ranges that far beyond your cutoffs. So if you have something like that, that probably means there was a mistake with your analyses. So good question, good job bringing that up, because that is extremely important. And that's something we'll develop as we go throughout the semester to identify some of those cases. Okay, any other questions or comments? Okay, very good question, very good question. All right, so variables that generally follow the normal distribution, as I mentioned on Monday, height and weight. So in general, people's height and weight follows a normal distribution. Standardized test scores, so things like the SAT, the GRE, even though they do have their biases, even though there are severe concerns with some of those tests, they do generally follow the normal distribution. Cumulative debt of college graduates does follow the normal distribution, that very few college graduates have 0 debt. And then you have a lot that are in, I don't know what the range is now, but let's say, 40,000, is that normal for college debt these days? Maybe more than that. Yeah, people are saying more than that now, 60,000, 80,000, 100,000. And then you have some people way out here that are doctors and lawyers that are, $300,000 in debt. So that follows a normal distribution. Very few that have 0 debt once they graduate college, a lot around the mean, whatever that is these days. And then you do have a few that fall way out here, lawyers and doctors that are something like $300,000 in debt. Okay. Other things that follow the normal distribution, advertising expenditure of firms. So companies, the amount of money they spend on advertisements tend to follow a normal distribution. You have very few companies that spend nothing on advertisements. So once again, normal distribution. Very few that spend nothing, a lot that spend somewhere around the mean. And then you do have some major companies that spend unbelievable amounts on advertising. And then the last one I'll briefly mention is rate of return on investment. That typically when you're doing investments, most of them will give you some return. Some of them will give you none, or even worse, some of them will lose your investment. And then some of them will get you incredible returns, such as Tesla recently, things like that. But most of the time with investments, they're going to give you somewhere around the mean in the return. So the point of mentioning all those is I want to point out that these fall into a lot of different domains of study. Height and weight is very different than test scores, which is very different than debt, which is very different than advertising costs. So we do see the normal distribution all throughout the natural sciences, all throughout business, all throughout the social sciences. So there is a reason to assume it in a lot of cases. Even though assuming it can give us big problems, we do see it quite frequently. All right. Also want to bring up the standard normal distribution. So the standard normal distribution is a special case of the normal distribution which the mean is 0 and the standard deviation is 1. So standard normal distribution is a special case of the normal distribution in which the mean is 0 and the standard deviation is 1. And when you have this, it makes it very easy to estimate the percentages of where your data falls. Because before, if we had the normal distribution and we were saying that our 68% falls within -1 to 1 standard deviation of the mean, we would then have to go calculate our mean. We would then have to see, all right, our mean -1 standard deviation equals this. Our mean +1 standard deviation equals this. So 68 falls between this value and that value. If we have a standard normal distribution, though, we know the mean is 0 and the standard deviation is 1. So then we could very quickly just say, all right, we know that 68% of our data falls within -1 standard deviation and 1 standard deviation of the mean, which would be -1 and 1, because the mean is 0 and the standard deviation is 1. So this will almost never happen in practice. You're never going to have data that just naturally has a mean of 0 and a standard deviation of 1. That's just never going to happen. But what can we do if we have a normal variable that we want to make fit the standard normal distribution? And the answer is we standardize our variable. We standardize our variable. And that's what standardizing our variable refers to. We try to convert it to a standard normal distribution. And this means calculating a z-score for each observation. Or standardizing our variable takes our mean and makes it 0, and standardizing our variable takes our standard deviation and makes it 1. So calculating a z-score for each observation. Okay. And then once again, with a standard normal distribution, we can easily determine the probability of a certain result occurring. With a standard normal distribution, we can easily determine the probability of a certain result occurring. So once again, going back to this picture that we visited 2 or 3 times now, we can very easily see, okay, so we have, a mean of 0, we have a standard deviation of 1. So if a particular value we have in our standard normal distribution has a value of -1, we can easily point to that value on the normal distribution and then easily calculate, okay, how many people fell less than that value. So once again, since our data is on a standard normal distribution, has a mean of 0 and a standard deviation of 1, we can then just quickly look at this bell curve and we can say, all right, if we have a value then in a standard normal distribution that has a value of -1, we can just instantly go to this right here and say, all right, if we have a value of -1, we can quickly see what percentage of people fall below that value when we're assuming the normal distribution. So we would just add up all of these frequencies to see how many people would fall below that value, in this case, -1. Another thing we can do with that, and this is the quicker way to go about that, is we can use a z-score table. We can use a z-score table, and this gets at the exact same thing. So these z-scores correspond to how many standard deviations away from the mean your observation is. So a z-score represents how many standard deviations away from the mean your observation is. So in this case, if we're using a z-score table, we could look and see, all right, let's say we're interested in how many people fall below 1 standard deviation from the mean. So once again, the z-score table tells us how many people fall below a certain value, what percentage of people fall below a certain value. So we just find a value on this table that we're interested in, and it'll tell us what percent fall below that value on a standard normal distribution. So if we're interested in a z-score, and you see the z up there, of -1, we'll just find it on this table. So if we go all the way down here, we see a z-score of -1. So z-score -1. And then the second, so this is the row, that's how you figure out what row you're using. And then the columns tell you the next percentage point you might be interested in. The column tells you the next percentage point you might be interested in. So in this case, let's just say we're interested in just a z-score of -1. We would then go to the row for -1 that I have highlighted down here. And since it's just -1, we don't have any other percentage we're interested in. So it would just be 0.00. So we see right here that for a z-score of for a z-score of -1, about 16% of people would fall below that. Roughly 16% of people would fall below that. So if we're looking at a normal distribution, a standard normal distribution, and we're interested in a value of -1, a z-score of -1, we could use this table and see, okay, about 16% of people fall below that value. Let's do another example just to make sure we're all on the same page. Let's erase that. Okay, so another example, let's make it slightly more complicated, is let's say we're interested in a z-score, a negative 2.09. Let's say we're interested in a z-score, a negative 2.09. So first we would find the negative 2, or the negative 2.0, because it's negative 2.09 we're interested in. So we would find negative 2.0, which is right here. And then we would go all the way over to find out what number we're interested in the hundredths place. So we had negative 2.09 we're interested in. So we find negative 2.0, and we go all the way to the 0.09, because that's the number we're interested in the hundredths place. So we go all the way to the end, and that's this number right here. That is this number right here. So if we're interested in a standard normal distribution, and we're interested in finding what percentage of people fall below a z-value of negative 2.09, we would then use the z-table, and from this we find that roughly 2% of people fall below that z-value, or fall below that z-score, because we found the negative 2.0, we found the 0.09, and that said it was 0.0183. So roughly 2% of people fall below that z-score, a negative 2.09. So that translates to, if we're looking at a normal distribution, roughly 2% of people fall below 2.09 standard deviations. So roughly 2% of people fall below 2.09 standard deviations away from the mean. Any questions about that so far? I know that that's confusing. I know that's it's hard, it's difficult, but are there any questions that can help clarify anything with that? Going once, going twice. Okay, so the important thing to know about this table, or one of the important things just to summarize, is this table will tell you what percentage of people fall below a certain value for a normal distribution. So whatever z-score you're interested in, it'll tell you how many people fall to the left of that value on this table. And to use it, you first have to figure out what number you're interested in and what decimal you're interested in the tenths place. So if we're interested in negative 0.1, that would be down here. If we're interested in negative 2.5, that would be right here, and so on and so on. But then we have to figure out what number we're interested in the hundredth place. Then we got to say, what number are we interested in the hundredth place? And that's what the columns are for. These columns differentiate what number is in the hundredth place. So in this case, if we're interested in negative 1.57, we would find negative 1.5, which is right here. And then we would go over to the 7 column, which is this number right here. We would see where those intersect. So if we're interested to find out how many people fall below a z-score of 1.57, or how many people fall below 1.57 standard deviations below the mean, then we would find negative 1.5. We would look at the column for 0.07, and we would see where those intersect, and that is roughly 0.06. So roughly 0.06 people fall below negative 1.57 standard deviations from the mean. Okay. Also, so this is the table for if you're looking at negative z-values. There are also a table for if you're looking at positive z-values. So this is the table if you're looking at positive z-values. And this tells you the same thing. It's how many people fall to the left of these z-values, but it's for things above the mean. So if you're looking at a normal distribution, it would look like this. So how many people fall below that value for the z-scores above the mean? So both of these tables are telling you how many people fall below, how many people fall to the left of that value, whereas the table we just looked at with the negative values were for z-scores below the mean. That's what we just looked at. This one tells us for the z-scores above the mean. And we see that because all of these z-scores are positive. Because all of these z-scores are positive, that's for how standard deviations or z-scores above the mean. So once again, just to give a quick example, if we're interested in seeing how many people fall below 3.25 standard deviations above the mean, So we're wanting to see how many people fall below 3.25 standard deviations above the mean. We could look at 3.2 because those are the first two numbers we're interested in. And then we have to look at the 0.05 column, which is this one right here. So we go 3.2, 0.05, where those intersect. And I believe that's that right there. So it's 0.9994 people fall below 3.25 standard deviations above the mean. So 3.25. So 0.9994% of people fall below 3.25 standard deviations above the mean. And this is once again assuming a normal distribution, but we often assume a normal distribution with our analyses. So that's what this would look like. This is what all these probabilities look like, both in theory and in practice. So any questions about that at all whatsoever? Okay, so now I'm going to see how well y'all can do at this. I'm going to once again break y'all into groups. So first off, these tables I just showed you are on the PowerPoint. So if you need to download the PowerPoint from Canvas, they are on PowerPoint. So go ahead, download the table. You can also get it through Google search. It's also in the back of your textbook. You have tons of ways to access it. The easiest way is probably just downloading the PowerPoint from Canvas. And I want you to use these tables on your own and see if you can find the probabilities associated with a value or z-score less than these numbers right here. Then also try to see if you can figure out on your own how to determine what percentage is associated with the value or z-score greater than these. So the first, less than, pretty much what we're doing. You're then going to have to figure out and see if you can do it on your own. Once again, I like experiential learning. I like students trying to figure it out on your own, having difficulties. It's part of the process before we come back together and figure it out together. But try to see if you can figure out using those tables how to determine percentages associated with numbers greater than that z-score. And then if you're feeling adventurous, try to figure it out on your own for z-scores between certain values, for z-scores between certain values. So once again, I'm going to break you up into groups, and y'all can figure out together using those tables just now how to find out the probabilities associated with z-scores less than, z-scores greater than, and then values or z-scores between two values. So any last questions about that? Okay, so I'm going to break y'all into groups. We'll probably do this for about, let's say 10, 15 minutes. But I'll join the groups. I'll be bouncing around. We'll see how it goes. So breaking you all into groups right now. And we have 46. So I'll break you all into 9 rooms. Create rooms. Open all rooms. There you go.
Muted.
Okay, so I was bouncing around the rooms. It seems like y'all did a fantastic job with that. So first off, good job. Almost every room I joined, I could hear people talking. And several of them, I've heard one person teach everyone else how to do it. So good job. I'm always impressed with y'all. Y'all always do a good job when we do breakout rooms. So thank you for your participation. So let's talk about how you should have gone about figuring these things out. Give me 1 second. Let me find where. Oh, there it is. Sorry, I'm trying to find my drawing tool that has now disappeared. Neat. Sorry, give me 1 sec. Sorry, 1 second. Okay. So I cannot find my drawing tool. So that would be a good time. Let's go ahead and take.
Are you sharing your screen for us?
Okay, thank you. I probably accidentally deactivated that. Thank you for pointing that out. Share. Ah, look at that. Thank you for whoever said that. I did not catch who said that, but you just now saved the class. So thank you for that.
That was definitely me, and you are welcome.
Thank you. I saw it that time. So thank you so much. Okay. So now let's briefly talk about how you should have figured it out. Which it seemed like I said, when I joined the groups, most of the groups were talking. Most of y'all seemed like you had it. So good job. So first off, the first three or the first four, this section right here was exactly what we were just now doing. All you had to do was just find the number on the chart, and that would tell you the value or the z-score less than. Because as we talked about, all of these z-scores tell us what percentage of the sample falls below a certain value. The next group of numbers was a value or z-score greater than. So can anyone tell me how your group figured out how to do this? Any guesses?
You subtract it from 1, don't you?
Exactly correct. Exactly correct. I believe that was Matt. So good job on that. Yeah. So since all of these tell us, since the numbers in the z-score table tells you how many fall below that z-score, we then need to find the opposite of that. We need to find the opposite of that because all of these percentages tell you how many fall below. We need to find the opposite. And the way we do that, as we found out last class, was the complement rule. So this is just an application of the complement rule. So we find, once again, the z-scores on this table will tell us how many fall below a certain value, what percentage fall below, but we're not interested in that. We're interested in how many fall above, how many fall above. We're going to use the complement rule because we also know that this entire distribution right here adds up to 1. So because we know the entire distribution of probabilities adds up to 1, we then know if we take 1 and we subtract how many people fall below that z-score. Oops, let me undo that. How many people fall below that z-score? That will then give us what percentage of people fall above that z-score. So once again, because the entire distribution sums to 1, because this entire range of probability sums to 1, if we take 1 subtracted by the percentage of people that fall below that z-score, oops, the percentage of people that fall below that z-score, that will then give us the percentage of people who fell above that z-score. So once again, if you need to find the value, the percentage of people that fell greater than that z-score or more than that standard deviation, number of standard deviations away from the mean, it's just simply 1 minus the percentage of people that fell below, which will give you the percentage of people that fell above. So you just find these numbers on that z-score chart and then take the resultant percentage and have 1 minus that percentage from the chart and that will give you how many people fell above. Okay. And the last one was value or z-score between. So can anyone tell me how you found the value or z-score between? Yep, and I see Sarah, I believe. Subtract the upper from the lower limit, and that is completely correct. That is completely correct. And the reason why that is correct is because, once again, these tables tell you what percentage of people fell below a certain value. So if you take how many people fell below the upper limit, which would look something like this, it will be all these people right here. But we're not interested in everyone who fell below the upper limit. So for this last one, we're not interested in everyone that fell below 1.96 standard deviations above the mean, because we don't want to include people that fell below 1.96 below the mean. So therefore, we want to cut out that other section. So therefore, we want to cut out people that fell right here, for instance. So to do that, we would identify how many people, what percentage of people fell below 1.96 standard deviations above the mean, which would be this right here, 1.96, and then subtract how many people fell below 1.96 standard deviations below the mean. So negative 1.96. So in this example, to find between, we just take the upper value, the upper z-score, the percentage associated with that upper z-score. So I guess you could upper z-score percentage subtracted by the lower z-score percentage. And that will give us between the z-scores. That will give us the percentage between the z-scores. So I wish I could draw this better, but I'm really bad at using a mouse to draw things. But to find the percentage between, you find the percentage that fell below the upper boundary. But since you don't want everyone, you want to cut out the people who fall in this other tail. You take the percentage associated below the upper boundary, subtracted by the percentage that fell below the lower boundary. And that cuts out those people down here. And that's how you get between. So in this example, between negative 1.96 and positive 1.96. Okay. And to look at a quick example of that, we could look at, I do not want to draw anymore. There. We could look at, once again, z-score table. So we could look at start with the upper boundary. So the upper boundary of that example we just now did was 1.9, which is this right here. And then 0.06, which is this column right here. We find the intersection, and that's 0.975. That's 0.975. So that says 97.5% of your sample falls below this value up here. So 97.5% of your sample falls below 1.96. However, we're also interested in excluding those people from the lower part of that. We wanted the between. So therefore, we need to go back and look at the negatives, because we're interested in negative 1.96 to positive 1.96. And we just find the same spot. Oops. Oh yeah, we need to erase that. Erase, okay. We therefore then just look for the same spot on the table, but we're looking for negative 1.96. So negative 1.9 right here. We then find the 0.06, which is right here. We look at where they intersect, and we find that right there. So the percentage associated with negative 1.96 to 1.96 would be 0.975 minus 0.025, and that gets us 0.950. So that means that 95% of our sample, 95% of our participants will fall between negative 1.96 standard deviations through, I guess that should, let me back up, through, so let's do a colon for that instead of a, so negative 1.96 through 1.96 will equal 95% of our sample. And we got that because the percentage with lower than 1.96 was 0.975. The percentage lower than negative 1.96 was 0.025. So subtracting that lower range from the higher range, we get 0.95, meaning that 95% of our sample falls within a z-score, a negative 1.96 to positive 1.96. And that's going to be something we're going to come back to throughout the semester because once we get into inferential statistics, we have this 0.05 cutoff. We're interested in a 0.05 level of significance. And that corresponds to wanting, or I guess if we want significance, finding z-scores outside of that range. Finding z-scores that are either less than 1.9 or negative 1.96 or greater than 1.96. And that skips ahead quite a bit, that goes forward, but that gives you the logic for once we get into inferential statistics, why we're interested in that 0.05 cutoff, why we're interested in z-scores lower than 1.96 and above, or sorry, lower than negative 1.96 and above 1.96. So that's how you find the percentages for both lower than, greater than, and between. Are there any questions about that? Any comments about that? Okay. One thing I would say is I think it would be reasonable for me to give on a test these exact questions. So just for your knowledge, I think it would be reasonable if I gave these exact questions right here. And if I gave you the tables, if I said, here's the z-score tables, find me what percentage falls below 3, what percentage falls above 1, and then what percentage falls between negative 1 and 1, I think that would be reasonable to have on the test. I think I should be able to expect y'all to do that. Okay, so if there's no questions, let's go, and I think that's all for this chapter. Yeah, I said that that's going to play a role in inferential statistics. Let's cover this extremely briefly because this is the end of this chapter. The very brief end of this chapter is we talked about the continuous uniform distribution and the normal distribution. The normal distribution being the most popular, continuous distribution. But there's tons of other continuous distributions. There are tons of other continuous distributions. One of them being the exponential distribution. And we're not going to cover that too much. We're going to cover this much more once we learn analyses that involve exponential distributions after the midterm. But this is what they look like. Exponential distributions look like this. And you can run analyses that assume your data has that type of shape. You can run analyses that assume your data has that type of shape. So if you're working with a data set that you know, hey, this does not follow a normal distribution, I am confident this does not follow a normal distribution, you can then explore other analyses that assume exponential distributions and many, many, many other types of distributions. And this is what an exponential distribution would look like, and you can assume this shape to your data. Things that have this shape are things like number of customers. A lot of companies have very few customers, and then very few have an extreme number of customers. Also, if you're working in a factory, number of defects in a production process has this distribution. Typically, when you're manufacturing something, you have very few mistakes, but there might be some processes that have tons of mistakes. But fortunately, most of them have very few. So it follows that exponential distribution. And personal income somewhat follows this distribution. A lot of people make a small amount of money, especially when you're thinking about the worldwide economy. A lot of people make very little money. And then once you move on out, fewer people make those extreme incomes. And also this can be used similarly to the normal distribution. We could look at the percentages, we could calculate z-scores if we're assuming the exponential distribution, because we can make certain assumptions about where the percentiles and z-scores lie. We're not going to do that in this class, but that's for your knowledge to know that, hey, we don't have to assume this normal distribution. We can assume other distributions, and we can perform analyses that assume other distributions, which is the important part. Okay, the book also goes over log normal distributions. We're going to talk about this once we get into inferential statistics, but I don't think we need to learn it right now. Let's cross that bridge when we learn about those analyses. But just know your book does cover log normal distributions. And here's other links if you want to learn more about those other distributions. Here's 2 links you can use to learn so much more about them. They're pretty good links, but we're not going to dig too much deeper into that before the midterm. Okay, so that's all for chapter 6. Any questions about chapter 6? Any comments about chapter 6? Okay, so let's go ahead and take a 10-minute break. So let's take a 10-minute break. and then we will meet again at 7:25, and we'll start with chapter 7. So let's take a 10-minute. Thank you. So yeah, so let's take a 10-minute break, and then we'll start with chapter 7. Okay, it is 7:26, so let's get back to the lecture. One thing I want to note first is I know a lot of y'all probably have not started thinking about your groups for the group paper, but I will say start thinking about that now, start getting your groups together now. Particularly, I've had several students reach out to me saying that, oh, we have a group of 2, we have a group of 3. We know it should be 5 or somewhere about 5, 4 to 6. How do we find more people? So I opened up a discussion board on Canvas. So if you do not have a group, go to that discussion board and make a post, or look at people that have already made a post. Just today, I've had 2 people contact me saying we have groups of 2. How do we find more people? They've already posted there. They're waiting people to contact them. So if you want to work with people that are hardworking that have already started, then hey, contact those people. They're going to be good group members. Don't wait till the last second and get on a group with a lot of people that procrastinated till the very end. So once again, if you need to find group, post on Canvas on the discussion board. I made a post just for group members to find other group members, and don't delay. So, okay. With that noted, let's go ahead and continue the lecture. So we are now starting chapter 7. So chapter 7 is a good chapter. We just now, or what we've done so far in the class is we've went over terminology, we've discovered best ways to visualize data, we went over descriptive statistics, and now we've discussed probability twice. So all of this laid the foundation for inferential statistics. Before we move into this though, we should really discuss sampling and populations. And I really like this lecture because I like the concept of sampling, how to get a good sample, what is a bad sample, and how does that relate to populations. Okay, so we already talked about this part, so I'm asking the class, what is a population and what is a sample, if you remember? So first off, what is a population? I saw a hand motion, but I haven't heard any talking yet.
It's the entire number of what you're looking at, or entire, available. I can't think of the word. Entire available observances.
You got the concept there, yeah. So the population is the group you hope to derive inferences about. It's the entire group that you might be interested in. So it's the entire group you might be interested in, the entire group you want to derive inferences about. So, it might be people, it might be companies, it might be products, it might be anything else, but it's the entire group that you're interested in. So for me, I do research on employees. So conceptually, my population might be every employee in the world or every employee that's ever lived. Because I study employees, I want to generalize to employees, but your population might just be every employee who works at your company. Or it might be if you are working for the government trying to help businesses in Alabama, it might be every business in Alabama could be your population. If you're a strategy researcher in the Mitchell College of Business and you're researching business strategy, your population might be every business in the world right now, or maybe every business in the United States. Regardless, your population is the group you're interested in, the group you want to derive inferences about. So therefore, a sample is a subset of the population. A sample is used to obtain observations, which are then used for statistical analyses. And if you remember, we collect a sample instead of a population, because a population is usually way too big. A population is usually bigger than anything we could ever dream about collecting. So instead we collect a sample and we hope that that can generalize to the population. We hope that our sample is representative of our population, that even though it's a smaller group, even though it's much smaller than our population, we hope that it represents our population pretty well. So therefore, choosing your sample, which is also called sampling, is among the most important parts of performing statistical analyses. I could teach you every advanced analysis. We could learn the most complex analyses imaginable, but all those would be rubbish if you don't know sampling. All those won't make a difference at all if you don't understand how to get a good sample. No analysis can turn garbage into gold, so we have to figure out how we can get a good sample so we can turn gold into gold, I guess, whatever figure of speech you want to use. But the point is we can't turn garbage into gold. Okay, so first we need to understand the concept of bias. And when we're talking about statistics, bias is the tendency of a statistic, which is obtained from a sample, to systematically over or underrepresent a subset of the population. It's the tendency of a statistic to systematically over or underrepresent a subset of the population. And we're going to talk a little bit more later about exactly what that means. But the important thing we need to know at this point is one of the primary sources of bias is from sampling. One of the primary sources of bias is from sampling. So our statistics can be completely wrong. Our statistics can be completely off base. Our statistics can be completely biased just from sampling errors, just from doing a poor job at sampling. So that's why we need to focus so much on sampling to make sure we can do a good job at it. So two types of bias we're going to talk about, and we're going to talk about a lot more than just this, but two types are selection bias and non-response bias. So the first type, selection bias, can anyone guess what that is?
You don't survey like a diverse enough group of people.
Exactly correct. Selection bias is a systematic underrepresentation of certain groups in the sample that are in the population. So it's a systematic underrepresentation of certain parts of the population. So your sample does not fully represent your population. It underrepresents certain subsets of that population. So it's when you have a sample that's not diverse enough. Can anyone tell me what are some examples of selection bias? What might be some common examples of selection bias?
Polling.
Sorry, say it again.
Polling for the presidential.
Okay, so polling, that's a wonderful example. Do you want to expand on that at all?
When you only poll a demographic of people in a certain zip code, let's say, instead of taking a wide range area.
Exactly, that's a wonderful example. So if we're doing political polling, we might just say, oh, it would be good enough if we just contact people in this one zip code. And we just assume that that's going to be representative of maybe an entire state. But as you can guess, that's often not, even though there's a lot of political polling companies that actually do that. That's usually not representative. That usually just one zip code is not representative of your entire state. You might accidentally pick a zip code that has a higher SES, that might have different racial demographic breakdowns, might even have different age breakdowns than your state. So therefore, it's very easy to have selection bias when you're doing political polling if you only select just one zip code, for instance. That's a very good example. Another example might be basic psychology research. If anyone here has ever taken a Psych 101 class, you probably had to be a participant in a research study. And often these have selection bias issues. Is that psych researchers very rarely are just interested in undergraduates. Typically, psych research wants to generalize to every person ever, that you're trying to identify these psychological phenomena that are universal. However, a lot of their studies are based on Psych 101 participants. They just give extra credit to these 18-year-old students in return for participating in the study. And that's because they're convenient. That's because they know they can get the sample. So therefore, they use those participants because they're easy to access. But as y'all can guess, 18-year-old psychology students often aren't representative of the entire population. They might have dynamics that are a little bit different. Things like if you ask an 18-year-old, about their family life, about their work life, that's going to be a lot different than a 40-year-old. Likewise, there's a lot of research on things like aggression. 18-year-olds tend to have a lot different aggression than 40-year-olds. 18-year-olds have a lot more hormones going on than 40-year-olds. So that's not representative of the entire population. So if you ever read a psych article that uses a Psych 101 sample, they always have in their limitation sections, the current results should be replicated with a more representative sample. However, this paper should still be published because da 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 da. So psych research has selection bias quite often. Okay, so the next one is non-response bias. Can anyone tell me what non-response bias is?
People don't answer the surveys.
Completely correct. Good job. Good job, Kimberly. So non-response bias is when there's a systematic difference between respondents and non-respondents in the sample. And as we'll talk about later, that systematic part is very important. So non-response bias is when there is a systematic difference between respondents and non-respondents in the sample. So it's if your people who actually took your survey are somehow systematically different than people who did not take your survey. So can anyone give me any examples of non-response bias?
Would the census be one?
Okay, so expand on that. How so?
Like, so the census is used to make decisions about how much money cities get and states get and stuff like that. So if people don't answer, it affects the outcome, I guess.
Yeah, so that definitely could be a case. Possibly the census is that maybe people who take the census just happen to be people that are, let's say, perhaps wealthier, maybe. People who take the census. One thing we often see in research is, this if it's voluntary, people who are more agreeable are more likely to take your survey. People that have more free time are more able to take your survey. So perhaps with the census, people who have more free time are more likely to fill out the census, whereas people who are busy, who are currently working excessively might not be able to take your survey. So you're going to have non-response bias, possibly in the census, based on people who work overtime hours versus people who don't work overtime. They don't have time to take your survey. And I see someone in the chat who said course evaluations. And yep, that's exactly one I was going to say. So good job, Noah. Course evaluations have non-response bias. Anyone who's ever taught a class knows that your course evaluations tend to look something like this, where you have people that really hated your class fill out the survey and people who really loved your class fill out the survey. But you have this whole non-response bias of everyone in the middle, because if you just sort of like the professor, you're probably not going to care enough to take the student evaluation survey. If you thought, they were fine, but I didn't love them, I didn't hate them, you're not going to feel a need to give feedback on that. However, if you really hated the professor, or if you really loved the professor, then you're going to take the student evaluations. So you're going to have non-response bias in student evaluations every single time. It always happens. And that's often why you see professors try to give extra credit, give some type of bonus for people taking student evaluations. This also comes up though in business. If you have any type of customer feedback, you're also going to see the same type of bias. A lot of restaurants have the little cards on the table that are customer feedback cards. If you've ever been a waitress or a waiter, every one of those feedback cards are going to have a distribution like this once you look at them at the end of the month. And you're going to have the customers who say, oh, I hate you, you did such a bad job. I asked for a refill, you took 30 minutes. They ignore that something major happened, that there was a fight in the restaurant, but they still leave that negative feedback. So those are the people down here. And then the other people are going to say, oh, I completely love this experience. You gave me a free meal. That was wonderful. So customer feedback is often the same type of distribution because we have this non-response. So anytime you're dealing with customer feedback, you're going to have non-response because all those people in the middle that just sort of like their experience aren't going to give any feedback. Okay, so therefore, because of that, if we try to perform analyses on that data, with either selection bias or non-response bias, we could get inaccurate results. We could get mistakes in our analyses. That our analyses will never tell us that. We're not going to run our analyses and it says, oh, look, you have non-response bias. Instead, we're going to run our analyses and it looks like everything ran correctly. But little do we know there's errors in our results. Little do we know there's bias in our results. So that's one reason why it's so important to talk about these concepts, so we can identify them before we even run our analyses, and hopefully we can correct them before we even collect our data. So to continue, so that gets into some of the problems of low response rate, and the big one was the one I just mentioned. But let's talk about some other ones briefly. Oh yeah, and one thing I want to note is on these slides, if you see a slide that has the asterisk right there, that means that our textbook does not cover this. That means our textbook does not cover this. Our textbook talks about how non-response bias and sampling bias is a problem, but actually doesn't tell us how to fix it. It just says, hey, your results might be complete garbage if these mistakes happen, but it doesn't tell you how to avoid those mistakes. So take note, if you have a copy of the textbook, any slide with the asterisk right here is not covered in the textbook. Okay, so to continue, what are the problems with low response rate? So first off, small sample sizes. As we'll learn when we cover inferential statistics, we need big sample sizes. We want to get as big of a sample size as possible. So if we have a small sample size, the main concern is even if our results should be statistically significant, small sample sizes will prevent us from finding significance. So we'll learn that. We'll talk about that a lot more later in inferential statistics. But even if our results should be significant, if we have a small sample size, we won't be able to find that significance. So therefore, if we have non-response bias, if we have smaller sample sizes due to low response rate, then therefore we might not even find statistical significance when it should be there. Also, another concern with that is it makes studies look unprofessional. So if you're an academic researcher, if you ever want to do academic research and you try to publish a paper where your response rate is something like 5 or 10%, then you're going to have huge problems. You're going to have huge problems. Any reviewer is going to say, no, that's garbage. You need to go back to the drawing board. And then the last one is low response rate insinuates there might be systematic non-response. And once again, systematic being very important. This is statistically the most important concern is when you have systematic non-response, that means your analyses are going to be inaccurate. And somehow if you have a low response rate, so once again, the response rate being, you asked X amount of people to participate, but you only had 5, 10% that said yes, that's low response rate. If you do have low response rate, if you do have something like only 5% of people that participated, if you can somehow show that it is, if you can somehow show that systematic non-response is not evident, then there's a chance you could be okay. So once again, we'll talk about this more in the upcoming slides, but if you do have low response rate, if you have something like only 5% of people respond, but you can somehow show that that's not systematic, if you can somehow show that systematic non-response is not evident, then you could be okay with a low response rate. You could go get by with a low response rate. However, that's going to be a large burden. That's going to be a really large burden to show that your low response rate is not systematic. That's a large burden to show. So therefore, it's better just ahead of time to try to make sure your response rate is high, to make sure your response rate is good, so you don't even have to go through these steps to show that it's not systematic. But we'll talk about all that in the upcoming slides. At this point, are there any questions or comments? Okay, so we'll continue. Okay, so when we're talking about response rate, what should we be shooting for? What type of response rate should we be shooting for? And if you're doing research, there was an article that reviewed business research. They reviewed business research articles, and they found the response rate to a mailed survey, whether paper or email, was roughly 41%. So the average response rate, if you're doing research, you should shoot for hopefully, somewhere around the mean of 41%. And they found the 30th percentile was 29%. So if you can get a response rate of 30 or above, then you should be okay for research purposes. If you can get a response rate of 30% or above, then you should be okay for research purposes. So if you're giving a survey to a company of 1,000 employees, if you're giving a survey to a company of 1,000 employees for research purposes, and you get 300 responses, then you should be okay, because that's a response rate of 30%. So for research, we're shooting for at least 30%. However, if you're in practice, if you're doing this for practice, if you're doing this for your company, where your company says, hey, we need to survey the employees to get an idea of what they're thinking of, to get an idea, are our employees happy? Are they sad? Are they angry? Are they frustrated? Then you typically want to shoot just for as many as possible. If you can get 100%, then yeah, that's what you want. The reason being is that if you're in practice, you want to be absolutely certain that you have a good feel for what are the perceptions in your company. That in research, sometimes we can get by with generalizations. In research, we want to generalize to the broader population, and we know we can't collect that broader population. But in practice, we might just want to know 100% for certain what's going on in this one company. In practice, we want to know with complete certainty, how do employees at this one company feel? So therefore, you're going to shoot for 100%. If that's possible, then great. If that's not, then you need to talk to your boss, you need to talk to your supervisor, sometimes CEO, and see, all right, if we can't get 100%, then what are we comfortable with? What are we comfortable with getting? With the students I've had in the past, they've been able to collect, 70%, 80%, even up to 90%, because when they work with a company. So try that, strive for that. That is certainly possible. So therefore, in short, if you're doing research, sometimes 30% or more is appropriate. if you're in practice and you're working for the company or working for the company, completing a survey, then you want to strive for that 100%. And if you think you're not going to be able to meet that mark, if you can't get 100% and you're doing this for practice purposes, then you need to have a talk with people to see, all right, what percentages are we comfortable with? So there's less clear guidelines with that. Okay, so to continue, we know response rate is important, but what can we do to improve our response rate when collecting data? And also, do our options differ based on the type of data we collect? So to answer those questions, first, okay, so what can we do to increase our response rate? So I'll leave this open to the class first. Do y'all have any recommendations? So if y'all have given a survey in the past, what do y'all think are effective approaches to increase response rate?
Any type of incentive.
That's a wonderful one. That is the best way. Any type of incentives is certainly going to increase your response rate. If you ever do academic research and you're trying to get college students to participate, no one participates for free. Time is money. But if you can tell people, hey, we'll give you $5 if you take our survey, they are certainly going to be more likely to participate. So wonderful answer. And I think that was Trey Johnson. So good job for that answer. Any other suggestions on how to increase response rate?
You have to have a captive audience. If you put them somewhere they can't get out, then.
Exactly correct. Captive audience. That's a wonderful reason. So having a captive audience. So sometimes you'll see with professors, if they're getting students to take surveys or evaluations of teacher effectiveness, you give it on the last day of class. And I think at South, we cannot require students to take it, but a lot of professors will say, hey, this is the last day of class. I'm going to let y'all out 30 minutes early. I would really appreciate it if you would right now open up that survey. Also, here's a bag of candy. You know, when you're done, take a piece of candy. You have a captive audience. They're more likely to take it then. I see someone in the chat say, yeah, an incentive. So yeah, certainly incentives. Keep it short. That's a wonderful one. Certainly keep it short. If you say, hey, here's a survey, and you give them a stack of papers, they're not going to want to take it. No one wants to take a huge survey. One example I've heard of in the past is when I was a grad student at Penn State. I worked with a professor, I took a class of a professor who she got something like a $10 million grant to study developments in Vietnam, and particularly how these rural villages were first getting electricity. And she was wanting to see how does that change their day-to-day life. And she had this huge survey. I saw a copy of it. It was like a book-long survey. And she would go to these villages and say, hey, I'll give you $100 if you take my survey. And to these rural villages, that's a ton of money. So she did it, and she would try to give the survey once a year, every year for 5 years. So she went the first time, gave them the $100, gave them the survey that was literally a book. They took it. The second year she went back and, they were like, oh, that survey was really long, but all right, we'll do it this time. And she said the third time she went back, the first house she went to, she knocked on the door and they had a $100 bill ready in their hand. And they said, no, here's $100. I'm going to give you $100 so I don't have to take this survey. So that's how much people hate surveys, is even though that was a ton of money, this person said, no, I will give you $100 if you quit bothering me. So that's a good one, very good one. Also, people said something people are interested in. Perfect example. If you're giving a survey for a company and it's something they're passionate about, then yes, they are going to respond. One consulting project I've worked on before was working with a union to figure out how people wanted to be paid. We had a response rate of almost 100% because everyone wants to have feedback on how they're going to get paid. That was very easy to get people to take that survey. Make sure they're aware of the purpose. Wonderful example. So in that example I just gave, the pay survey, we had a cover letter that said, this is the survey that determines your pay. Please fill out the survey. And once again, everyone took it because they knew this was the pay survey. Advance notice and reminders. So good job on that. So if you tell people ahead of time, hey, you're going to have a survey. It's going to come in 1 week. Please complete that survey. That's going to come in 1 week. They're going to be more likely to complete it. And then, yes, send reminders. Good suggestion. If you tell people, hey, here's the survey, you then send them the link. And then if they don't complete it, send them reminders. They're going to be more likely to complete it. I'm going to be very curious. I think it started already. Do y'all have to take the daily surveys about COVID symptoms? Do y'all have that yet? Yeah. So I think like you're supposed to take it every morning, something like that, or at least once a day.
Every time you come to campus. Every time you come to campus, I think.
Okay, so every time you come to campus, yeah. And some people saying every 3 days, so that might fit with your course schedule or something like that. Yeah, I'm going to be very interested to see how do they increase that response rate, but also if someone doesn't take the survey, how often are they going to send those reminders? And what are they going to do to make sure people aren't just showing up to campus without taking the survey? I know there's some implementation of that in place, but I'm going to be very curious to see how those current plans affect response rate. We'll see, and maybe that'll be part of class in a month or so. Okay, so I think you all covered the big one, give advance notice, topic salience, also personalization. Y'all would be amazed with if you send a survey that says, hey, Matt, can you take this survey? People are much more likely to take it as opposed to Dear South Alabama employee. I received a survey or invitation to take a survey one time that just said, Dear person. Of course, I deleted that immediately. Who says Dear person? So personalization, identification numbers will also increase response rate. If you know people are assigned with certain numbers and they give the survey back and you know which numbers are completed, they're more likely to do it. Sponsorship is a big one. And sponsorship is also big if you're doing academic research. If you're ever doing academic research and you send an email that just says, hey, my name is Matt Howard, please take my survey, no one's going to take it. So therefore, whenever I do research, I send an email with a South Alabama logo on it. I say, hey, my name is Matt Howard. I say, my name is Dr. Matt C. Howard. I'm a professor at the University of South Alabama. People are much more likely to take my surveys because they think I'm more legitimate. They see the South Alabama logo. They know that I'm just not a weirdo who's going to do weird stuff with their data, or they assume I'm not a weirdo. We'll ignore that for now. Incentives, we already covered incentives, and also personally deliver and obtaining surveys. If you give the surveys by hand and you take them back by hand, people are more likely to complete them. But are there any concerns with that or any of these other ones? Do you all think there's any concerns with any of these?
Yeah, identification numbers. If someone doesn't want to be identified, it could be, they could think it'd be retaliation.
Exactly, 100% right. Yep. So identification numbers are also often very touchy, that if people think they're being tracked somehow, they're less likely to be honest. They're less likely to be authentic and possibly less likely to take your survey. Yeah, so if an employee satisfaction, if an outside source is, if it's identifiable, so often with things about employee satisfaction, we'll not only ask things like, do you enjoy working at this company, but it says things like, do you like your boss? Do you enjoy your boss? So if anyone thinks that can ever be traced back to them, they are not going to answer that, or they're not going to answer honestly. And you have to be very careful when you have identification numbers, because I have seen instances in the past and heard of instances where people have thought that it was anonymous, but it wasn't whatsoever. Particularly, I had a student who she works for the state of Alabama. I don't remember exactly what she does, but they had a state of Alabama survey that they were trying to just ask all government employees, hey, what do you think of working for the government? And one of the questions was, what do you think of your immediate supervisor? And then when they reported their results, they gave the average of all the departments. And they said, on average, this department gave their supervisor a 6. On average, this one gave them a 5, so on and so on. It turns out some departments only have 1 employee. So there are certain departments where they could go back and say, oh, I know this has only 1 employee. I know this person now hates me. Caused huge concerns, huge problems. Yep, and the person in chat just now said what I was leading towards, so good job on that, Vanessa. Personally delivering and obtaining surveys can lead to people not being honest. So even if the survey is completely anonymous, even if your name is not on it, if I know I'm handing my survey back to someone and they're going to have it in their hands, obviously they're going to know that's from me. So therefore, people are going to be not honest if they think that someone's going to have their survey in their hands. So therefore, there's a lot of ways you have to go to get around that. Particularly if you're obtaining surveys, paper surveys, we would want to do something like have a big box and have everyone put their survey in the box so we don't know who put their survey in, where it fell in the stack, so on and so on. You very rarely want to actually have the survey in your hand. You want to have it mixed with other surveys. Okay, so wonderful job. Y'all have all the big ones. Y'all identified the major concerns. So good job. Give yourself a pat on the back. Okay. Also, although we can help ensure that people take our surveys, we cannot always ensure they complete them entirely. And this is a huge concern. This is called missing data. So missing data is when people might take your survey, but they might not answer every question, or people might receive your survey, but they don't answer every question. So what do we need to know about this? So first, I want to tell you that data can be missing at the item, construct, or person level. So data can be missing at the item, construct, or person level. So item level missing data is when the participant doesn't answer an individual item within a scale or within a construct. So item level missing is when we might have 6 items that ask about job satisfaction, and a participant just skips one of those items. So item level missing data is when we have, let's say, 6 items that measure job satisfaction, and a participant just skips one of those items. The next one is construct level missing data. So construct level missing data is when a participant doesn't answer any items for the entire construct. So this might be, once again, if we have 6 job satisfaction items and the participant skips all 6 of those items. So whereas item level missing data is when they just skipped one, construct level missing data is when they skip all the items in a particular scale or all the items used to measure a particular construct. So in this example, skipping all 6 job satisfaction items. And then the very last one is person level missing data, is when the participant doesn't answer any items in the entire survey. So this is when you know the participant received the survey, and however they chose not to answer any of the items. So you know that they received it, but they chose not to answer any of the items. And from my experience, item level and person level almost always happens. Item level, you almost always have participants that accidentally skip an item, that just miss an item here and there. And also you almost always have participants that might receive the survey and they just choose not to return it or choose not to fill it out. And then on the other side of the coin, construct level missing data is much less common. It's much less common to have people skip an entire construct. Usually it's like this accidental missing data, accidentally skipping an item, accidentally forgetting to fill out the survey, whereas a construct level is usually more intentional. Construct level is they choose to skip over that entire section of items. Okay. So also in conjunction with these, so in conjunction with item, construct, and person, we should also know that data can be missing completely at random, missing at random, or missing not at random. And we're only going to talk about the first and last one. So these could apply to any of the 3 types of missing data we just talked about. So data can be missing at the item level, and it can be missing completely at random or not at random. Data can be missing at the construct level. It can be missing completely at random or not at random. And data can be missing at the person level, and it can be completely at random or not at random. So these are not like or, this could be like and/or, I guess. That it can be missing at the item, construct, or person at both random and also not at random. So therefore, what are these? Missing completely at random is when the missing responses are truly at random. So missing completely at random is when the missing responses are truly at random. So if we're talking about item level missing data, this might be where a person is filling out the bubbles and they just completely randomly, just due to random chance, skip a bubble. There's no rhyme or reason there. It's completely accidental. They just randomly skip a bubble. So that would be item level missing completely at random. On the other side of the coin, missing not at random is when the missing responses are due to the responses of the item itself. So missing not at random is when the missing responses are due to the responses of the item itself. So this is when this is a case of systematic non-response. So this is extremely important. This is when there's systematic non-response, and this is more likely to bias your statistical results. This is more likely to bias your statistical results. And this is missing not at random. So an example of missing not at random might be if we're giving an employee survey, and we might ask our employees, do you smoke marijuana? People who do not smoke marijuana, they're probably going to say no. They'll be very open with saying no. However, employees that do smoke marijuana will be more likely to just skip that question, or in some cases more likely to lie, but employees who smoke marijuana are more likely to skip the question. So that would make it missing not at random, because the missing responses are due to the responses of the item itself. People who would be more likely to say yes are more likely to skip that item. The same would be true with a an entire scale on supervisor liking, how much you like your supervisor. You might have construct level missing not at random. You might have construct level missing not at random. Then you might have participants that they get to those series of items about how much you like your supervisor. And if you really hate your supervisor, but you think there's some chance they might see your answers, you might just skip all of those items. You might just skip that entire section. So that would result in construct level missing not at random. And then the last one, missing at random. Don't worry about that one. We're not going to talk about that one. In this class, we're just going to talk about missing completely at random missing data and missing not at random missing data. Okay. So are there any questions about? Okay, so I have a problem in which job applications ask my ethnicity, which is Hispanic or Latino, but then they ask my race and I leave that one blank. That's interesting. That's a very interesting one. So in that case, I would say that would be missing not at random, I would assume, because with the race question, your non-response is in part due to your race or ethnicity. So therefore, you're choosing not to answer. Yeah, you leave that one blank on purpose. So that's a wonderful example. That's a great example. So in that case, it'll be missing not at random because you're choosing not to respond based on your answer to the response or based on your possible answer to that question. So that's a wonderful example. That's a great example. And we see that all the time with asking questions about race or ethnicity on surveys, that if those questions are not asked properly, you're going to get tons of non-response. You're going to get tons of missing not at random responses. So that is one thing. If you're ever making a survey and you want to include race or ethnicity questions on it, make sure you reach out to someone who knows how to answer those questions, or sorry, knows how to ask those questions correctly, because otherwise you're going to get a lot of non-response. So great example on that, Hector. Good job on that. Okay. So why do we care about this? As I already mentioned, missing data might cause your results to be biased. So therefore, your standard errors and hypothesis tests might be inaccurate. So if you have missing data, your standard errors and your hypothesis tests, aka your inferential statistics, might be inaccurate. And of course, that's bad. You don't want that. And that is much more likely to occur when you have systematic non-response. That's much more likely to occur when you have systematic non-response. So if you have data that's missing not at random, you're more likely to have biases in your standard errors, your hypotheses, and your inferential statistics when it's missing not at random. Okay. One thing to note, there's a lot of methods to address missing data. This is literally a career for some people. I know of PhD grad programs where you can take multiple classes just on how to address missing data. There are quantitative psychology programs that people go to grad school. They have an entire PhD that's almost entirely focused on missing data, and their entire research career is just methods to address missing data. So if you're interested in that, go to a quantitative psychology conference. They are not the most exciting thing ever. I have been to one. I have only been to one. There's a reason I've only been to one. So you get the point. For now, we're not going to worry about ways to address missing data. Instead, we're going to consider why missing data might occur and how to preemptively try to reduce missing data, because it's much easier to reduce your missing data than it is to address your missing data. So let's talk about, do I have this here? Yeah. So we already talked about this, I guess, to the extent I wanted to cover it. We already talked about why we might have item, construct, or person level missing data. So item level might be if someone skips a question by accident, but item could also be like Hector brought up. You might not have a response you want to give, or you might not, the question might not be asked in an appropriate way. So therefore you might skip it. You could also have construct level missing data if you don't want to answer the question because you think it might have bad ramifications. So things like the supervisor example, if you think your supervisor might see that you said they suck, then you might skip that entire set of questions on supervisor performance or how much you like your supervisor. And then person level, if you think the entire survey might have something in it you don't want to answer, you might just choose not to take the entire survey. You might just choose to leave the survey in your desk and never return it if you think the entire survey might have issues that you don't want people to see. And then once again, completely at random tends to be just accidental mistakes. You accidentally skip something. whereas not at random is when there's a systematic cause that caused you to skip that item, that construct, or the entire survey. So once again, not at random is systematic, and that's important to know. Okay, so therefore, based on those concerns, we really need to think about how we obtain our sample. We really need to think about how we obtain our sample. And we're going to talk about 4 different probability sampling methods. These are simple random sampling, systematic random sampling, stratified sampling, and cluster sampling. Those are the 4 we're going to talk about. So the first one is simple random sampling. Can anyone tell me what is simple random sampling? Any guesses? Any guesses what
Is
simple
it when
random?
it's like just completely random?
Yeah,
like-
yep, there you go. It's when it's completely random. It's a completely random method in which everyone in the population has an equal chance of being sampled. So good job on that, Vanessa. Completely random method in which everyone in the population has an equal chance of being sampled. So to do this, you would somehow hopefully have a list of everyone in your population or a way to know everyone who could be in your population. And you just use a random number generator. And you just click the button and it identifies, all right, pick person 1,372. You pick that person. Click random number again, pick whatever next random number comes up, so on and so on. So it's completely random. It's truly random. So simple random sampling is when you have equal chance of everyone in the population being sampled, and you just randomly select those people. I guess I'll talk about this briefly. One way people used to think about this would be you just get the phone book, and then you randomly pick people out of the phone book. Why would that possibly not be random, though? Why would that possibly not be random?
Because a lot of last names, there could be last names that have multiple. I mean, I don't know. It could be. I don't know. It just sounds problematic for a lot of reasons.
It does sound problematic. There are problems there. Anyone else want to give it a shot?
You would have to have a phone for that to work.
Exactly. You have to have a phone for that to work. So picking names randomly out of the phone book, that's not going to be your whole population. Not everyone has an equal chance of being sampled because there's a lot of people that just aren't going to be in the phone book. So therefore, we no longer say that as an example. That used to be more true, in the 50s and 60s. So if you get a stats textbook from back then, they would still use that example. But these days, a lot of people just don't appear in the phone book.
They don't even publish phone books anymore, do
they? That's a good point. I have no idea. I think I have one, maybe. I don't even know if I have one. So it might not even exist anymore. So therefore, don't think about phone books when you think of this. Try to think of if somehow you had a separate list of everyone in your population, and you could truly random sample from all those people. Okay. The next one is systematic random sampling. So Braden says, fun fact, my parents picked my name out of the phone book. So very nice. So at least phone books helped one person in this class. Glad phone books have a positive influence on one person. So, okay. Can anyone tell me what systematic random sampling is? Yep, take the whole population and every certain number of participant is selected, and that's completely correct. So once again, we would theoretically or hopefully have a list of everyone in the population, and then we choose every nth participant. So we might say, all right, our population has 30,000 people. We want to select 3,000 of them. So we select every 10th participant. So we just go through the list, 1, 10, 20, 30, 40, so on and so on. We just choose every nth participant. Maybe if we know we want to select. Sorry, say it again. Okay, maybe that was just an accidental unmute. But yeah, so you select every nth participant. So it might be every 10th, every 100th, maybe even every 1,000, if I could say that word, 1 out of every 1,000 people. Either way, you have some number that's regular and it's an interval. So it's not truly random, because truly random is just completely random numbers. There is a pattern here, but we would assume that it's roughly random, that it's roughly systematically random. Hopefully your list doesn't have an order to it. Hopefully the people listed in your list are randomly distributed throughout that list. So therefore choosing every 10th person does get at that randomness, but it's not purely random, Okay. The next one is stratified sampling. What is stratified sampling?
Is it when you take a sample from different demographics within the population?
There you go. Good answer. Very good answer. Good job, Diana. So the population is divided into groups based on a characteristic, and then participants are randomly selected from each group. And it's usually used to ensure that all ranges of a characteristic are included within a sample. So population is divided into groups based on a characteristic, and then participants are randomly selected from each group, and it's used to ensure that all ranges of a characteristic are included in the sample. So you might do it based on age. So you might, in your population, divide your group into ages from 0 to 10, 10 to 20, 20 to 30, 30 from 40, so on and so on. And then you take 10 people from each age group. Then you might take 10 people from each age group. And that would help ensure that you have people from each of those age categories. You have people that represent each of those age categories. Also, this is one quick note, is you also could you could make categories like that. So 10 to 20, 20 to 30, 30 to 40, and so on and so on. And theoretically, you don't have to select the same number from each group. You don't have to select the same number. So if you think that age has a bell curve shape, you could select in this bottom group maybe 5 people, the next one maybe 10, the next one maybe 20, and then go back and select 10 again, and then select 5 again, and try to get a bell curve shape based on age. And that kind of goes beyond what you really need to know, but just know that if you're doing stratified sampling, you don't absolutely have to select the same number of participants from each group. You could select, if you want to try to mimic a bell curve, a different number of people from each group, maybe 5 from the first one, 10 from the second, 30 from the third, but then go back to 10 and then 5 again, if you want to try to approximate a bell curve. So that's the example for age. Another example is when I was an undergrad, I did research on college student drinking behaviors. So what we wanted to do is we wanted to have 2 different groups and have them do a certain intervention where we would show them a video and saw if that affected their weekend drinking at all. So we knew that we would have 30 people in each group, but we wanted to make sure that one group just didn't happen to have all the heavy drinkers in it. So therefore, what we did with our 60 students is we divided them into categories based on their drinking. And it was something like people who drank not at all, people who drank 1 to 2 drinks per week, people who drink, I think it was 3 to something like 6 per week, and then people who drank 7 or more. And then we made sure that out of this, half of the zeros went to each intervention group, half of the 1 to 2 went to each intervention group, and so on and so on, because we wanted to make sure there was an equal balance between the 2 intervention groups based on the drinking. So that helped ensure that we just didn't randomly have one group that had all the heavy drinkers and one group that had all the light drinkers. So does that make sense? Somewhat, sort of. Okay, I see people saying yes. Did everyone start drinking? Yes, we actually did have some people drink more after. Yeah, that's part of what the study showed is that's kind of, I don't want to say we expected that because that would sound really bad. But what the intervention actually was is, you all probably experienced this in high school, is often people come in and they put the drunk goggles on and they make you walk and they make you like, drive a remote control car. We wanted to see how that actually affected drinking because we found that there wasn't really a good study on that yet. And we actually found that some people drink more. And our logic behind that and what our data supported is, when you do that activity with the goggles and people are around you, everyone laughs. Everyone has a great time. They're like, ha, 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 ha. When you're drunk, you fall over. When you're drunk, you can't drive a car. So therefore, what are you going to want to do that weekend? You're going to want to get drunk because the drunk goggles were so fun. And that's pretty much what we found, that students had a good time putting on the drunk goggles. So then a lot of them drank more on the weekend. So drunk goggles, not always the best idea. Some interventions are fine, but not always the best thing if the person making you put them on are trying to make you have a good time. So good question, Colton. Good job on that. And I'll also say that we did have 2 participants in the sample. We made sure we put in separate groups because we had 2 students who claimed, assuming they told the truth, they claimed that they drank, it was over 140 drinks a week. So they said they averaged 24 pack a day. So if you're one of those people, you need help. Just putting that out there. So, okay. So also the next one is cluster sampling. Cluster sampling, I'll go ahead and tell you. Cluster sampling is the population is divided into clusters, and then participants are randomly selected from the clusters. and this is usually used for convenience. This is usually used for convenience. So an example might be if we're looking at Mobile, we might separate Mobile into different zip codes, and then we only select from 2 zip codes, because we might just assume that, hey, those 2 zip codes are representative enough of all of Mobile, so therefore we're only going to select from those 2 zip codes. So once again, dividing the population into clusters, and then only selecting from some clusters, such as zip code. Mobile, I think, has what, 6, 7 zip codes? I don't know, to be honest. And then only selecting from 1 or 2 of those zip codes. So a visual illustration of the difference between stratified sampling and cluster sampling looks like this. Stratified sampling, we separate it into multiple groups, and then we select some people from each of those groups. Whereas cluster sampling is we separate into groups, but then we only sample from some of the groups. Then we only sample from some of the groups. So in this, we might have 6 different ages, and then we select some people from each age group. Cluster sampling might be something like we have 6 different zip codes, but then we only sample from some zip codes. Then we only sample from some zip codes. So, and I think that picture describes it much better than I ever could. So if you get confused about this, go back, look at that picture, think about it more, shoot me an email. I'm happy to talk about it further. Any questions about any of that so far? Okay, so let's continue. So which one of these is the best? Conceptually, simple random sampling is the best. Typically, if there's any systematic characteristics of the data set that you should represent, if there's any characteristics of the data set you should represent, conceptually, theoretically, simple random sampling should be able to get at those characteristics. Simple random sampling should be able to get a sample that has those representative characteristics. It doesn't always happen because there's randomness involved, but simple random sampling on average should represent your population, or sorry, simple random sampling on average should get a sample that on average represents your population. So simple random sampling we often think of as the best. However, in addition to probability sampling methods, there are also non-probability sampling methods. So we just covered the probability sampling methods, but there's 2 non-probability sampling methods I want to talk about. And these 2 are voluntary sampling and convenience sampling. So voluntary sampling and convenience sampling are the non-probability sampling methods. So can anyone tell me what is a voluntary sample? What is a voluntary sample?
You get people to volunteer to be in the sample.
Exactly, exactly correct. So people self-select for the sample. People volunteer for the sample. So one question you might ask yourself is, isn't pretty much every sample a voluntary sample? No one's forced to take a survey? And the answer is, to some extent, yes, most samples are voluntary samples. Even if you're required to from work, no one's going to threaten you with life or death to take a survey. But typically when someone refers to a voluntary sample, that means a sample that people have abundant opportunity to say no. It's not like, you know, your supervisor is saying, hey, you have to take the survey. If your supervisor is telling you to take a survey, that's probably not a voluntary sample. We're not going to refer to that as a voluntary sample. Instead, a voluntary sample might be you receive a link in your email that says, hey, here's a link, can you please complete that survey? That's going to be a voluntary sample because you can easily say no to that. Whereas it's much harder that if your boss is right there in front of you asking you to take a survey, it's much harder to say no. So therefore, when we refer to a voluntary sample, that typically means a sample that there's no punishment, there's no repercussion, whether official or unofficial, to saying no. So it's different than your boss directly asking you. It's something more like you get an email with a link and it's very easy to ignore that. It's very easy to say no. That would be a voluntary sample, and it's very easy to say no. Okay. The next one is a convenience sample. So what is a convenience sample? Any guesses about convenience sampling?
Like a convenient sample.
Yeah, exactly. It's an easy sample. It's a convenient sample. It's a sample made up of easy to reach people. It's a sample made up to easy to reach people. So you might ask yourself, well, isn't almost every sample a convenient sample? And the answer is yeah, to some extent, if we're being fair. often we don't make a list of the whole population and say, oh, we need to sample some people from the US, some from Brazil, some from China, some from Japan. No one does that, or very rarely do people do that. So to some extent, almost every sample is a convenient sample. But typically when we refer to convenient sampling, we're referring to sampling where we're just asking people that are nearby. Typically when we're referring to convenient sampling, we're asking people that are nearby. So a convenient sample might be we go to the dorms on campus and we have a clipboard and we just ask students as they're walking by, hey, can you take the survey? That's typically what we're referring to when we say a convenient sample. This might also be we go to the mall, we take a clipboard to the mall, and we just ask people walking by, hey, can you take this 5-minute survey? That's a convenient sample. Or even posting a link on your Facebook page. We would also call that a convenient sample. So a convenient sample is made up of easy to reach people, and that's typically what we're referring to when we say convenient sample. Okay, so this is some of the thoughts we're going to close on today. Is how does a sample tell us about a population? Two things we're going to talk a lot more on Monday. We're going to cover this very thoroughly on Monday, but I want to get an introduction to it now. Is we need to talk about parameters and statistics. We need to talk about parameters and statistics. So parameter is a statistical attribute of a population. It is a statistical attribute of the population. And parameters are constants because they describe a single reference, and this value is unknown. So a parameter is a statistical attribute of the population, and typically the easiest one would be to think about would be something like the mean of the population for a certain variable. So the easiest one to think about would be something like the mean of the population for a certain variable. So if we're thinking about every person in the world, we could think about their mean height. We could think about the mean height of everyone in the world, and that would be a parameter. The mean height for everyone in the world, because that's our population we're interested in, that could be a parameter. And that's a constant because it's there's only one value that would be the correct answer for that. There would only be one value that's the correct answer for that. That in this exact second, at this exact moment, there's only one number that would be the mean height of everyone in the world. And when we're thinking about parameters, we're thinking about these split-second things. We're not thinking at this point about it longitudinally. We're thinking about these split-second things. So the height of everyone in the world at this exact moment is a constant because there's only one number that would be the correct answer to that. A statistic, however, is a statistical attribute of samples. A statistic is a statistical attribute of samples. And when we think about statistics, we think of them as random variables. So parameters are constants. On the other hand, statistics are random variables or random numbers. And that's because the value of a statistic depends on the chosen random sample. That's because the value of the statistic depends on the chosen random sample. If we get a sample A, 100 students on campus, and get their mean height, that value is going to be different than if we get sample B, that's the mean height of 100 people we got from the mall, and that number is going to be different than C, that might be a different 100 people we got from the mall. So because because the statistical attribute of the sample is going to depend on each sample, because that's going to be different from each sample, we consider that a random variable. We consider a statistic a random variable. And as we've talked about before in class, we try to identify this value. Parameters, so attributes of the population, are unknown. We can never know those. We can never know a population parameter with certainty. However, we can identify a sample statistic. We can identify a sample statistic. And also, whenever we use a sample statistic to estimate a parameter, it's called an estimator. And a particular value of the estimator is called an estimate. Estimate. So therefore, if we collect a sample, we get a sample statistic, and we try to use that sample statistic to estimate the population parameter, we call that an estimator. And that particular value, so such as a mean height of 7 foot 4 inches for our sample, would be the estimate. Okay. So I know that's confusing. I just want to get you an introduction to these concepts before we talk about them thoroughly on Monday. Okay. So let's think about the following examples. So let's say we wanted to know the mean age of students on campus. So we wanted to know the mean age of students on campus. So we calculated the mean age of 30 students we collected to figure this out. So in this example, first question, what would be the population parameter? What would be the population parameter in this example? So first off, what is the population in this example? What's the group we're interested in?
Students.
All students on campus.
Yep, all students on campus is our population. That is correct. All students on campus is our population. So that right there is our population. So therefore, what would be the population parameter that we're interested in?
The mean age, the age.
Yep, that's correct. The mean age of all students on campus. So because all students on campus is the population we're interested in, our population parameter in this example is the mean age of all students on campus. So good job on that. And that's considered a constant because there's only one value that's the correct answer for that. There's only one value that's the correct answer for that. In this split second, there's only one value that would be the mean age of all students on campus. And that's why we consider that a constant. So what would be the sample statistic or the estimator? So first off, what is our sample in this example?
The 30 students.
Yep, completely correct. So in this example, our sample is the 30 students we collected. So good job on that. And then what would be our sample statistic? Any guesses for our sample statistic?
The mean of the 30 students?
Yep, completely correct. Good work on that. Good job. The mean of the 30 students, the mean age of the 30 students. So in this example, our population is all students on campus. Our population parameter is the mean age of all students on campus, whereas our sample is the 30 students we collected, and the sample statistic is the mean age of those 30 students. So here's that. And then I'm going to say this briefly. Statistical proofs have shown that the expected value of the sample mean equals the population mean. So statistical proofs have shown that the value that we would expect on average of our sample mean equals the population mean. So the expected value or the average value of the sample mean equals the population mean. So what does this actually mean? What's some things we should know about this? So if you remember the law of large numbers, if we were to obtain an infinite number of sample means, then the average sample mean would be the population mean. Because once our sample size gets large enough, our observed probabilities equal the actual probabilities once the sample size gets large enough. So if we had an infinite number of sample means, the average sample mean would equal the population mean. And that's why the expected value or the average value of the sample means do in fact equal that population mean. Because of this, we often assume a sample with a relatively large sample size is a relatively good estimator of the population mean or any other population statistic we might be interested in. So because of this, we often assume that a sample with a relatively large sample size is a relatively good estimator of the population mean or any other statistic we might be interested in. So, and that's all based on the law of large numbers, based on the expected values of the sample and the population parameter. Okay, so therefore that's where we're going to leave today. We're going to cover this more on Monday. So chapter 7 also covers some of these more ideas. If you're interested in the nuts and bolts and statistics, go back, read chapter 7 of the textbook. It covers a lot of the interesting nuts and bolts. We're not going to cover it as thoroughly as the textbook does because we're more focused on application, but it's there if you want it. And yeah, and we're going to leave off on the question, since we know the sample estimate is not perfect, what do we do? If we know the sample estimate does not perfectly describe the population parameter, what do we do? And that's what we're going to learn on Monday. That's going to be the focus of Monday's lecture. So thank y'all for hanging in there. This was a good lecture. I appreciate all your hard work. Y'all did a great job today. So wonderful job. Thank y'all so much. And I will see y'all on Monday. So have a good weekend. So thank y'all very much.
Thank you. Have a good one as well.
Yep.
Thank you. Have a good one.
Thank y'all.